Hey guys, so today we are going to do a short review and summary of some of the main points of class so far. We'll kind of take a step back and look at the big picture ideas for today to start reviewing for your midterm, which is coming up soon. So physical oceanography, we've learned, is a quantitative description of the ocean's properties and the movement responsible for the distribution within and at the boundaries of the ocean. The important properties that we've discussed so far are pressure, density, temperature, and salinity. Note that pressure is somewhat unique here because we don't specifically use it as a tracer like the other properties discussed. Pressure doesn't get vected around like temperature and salinity do, and we don't really use it as like a distinguishing property of water masses, kind of. But it's still a really important property of the ocean. We know that we measure pressure as a proxy for depth in the ocean, and changes in pressure, pressure gradients, work to drive fluid motion. So in the ocean, hydrostatic pressure is the pressure due to the force of gravity, or the integral from the surface of the ocean to some depth z of the gravitational acceleration times the density at depth z. This integral simply represents the sum of the weight of the overlaying fluid at some depth z. From this equation, we can make our incompressible assumption, which again means that density is constant and therefore not changing with depth. So we can remove density from the integral and solve for pressure at depth z. So by solving this integral, we can see that our hydrostatic pressure equation in the ocean is simply negative g times the average ocean density times the depth z. And we need to add this to the pressure of the overlaying atmosphere. It's easy to see from this equation that pressure varies linearly with depth, and so we often use pressure as a proxy for depth. Okay, so the second property that we have discussed quite a bit in class so far is density. We know that density is a mass per unit volume and is a function of temperature and salinity. We think of a stable water column being one in which density increases with depth so that light waters sit on top of heavier waters. We've also learned that in the ocean, while changes in density are very important to ocean dynamics and fluid flow, density changes by such a small percentage that we can make the incompressible assumption. So when we derive the conservation of mass equation for incompressible fluid, we can neglect the terms in which density changes in space or time, leaving us with the continuity equation. Okay, so the third property we discuss quite a bit is the temperature of the ocean. We talk about the ocean heat budget, which includes all the inputs and outputs of heat from the ocean, as well as the movement and distribution of heat around the globe. So our equations for ocean heat budget should look somewhat familiar as they relate to the equations of motion that we have discussed at length so far. We have the left-hand side of the equation, which we have seen before. This is our material derivative, or our Lagrangian rate of change of temperature. Again, this is like we are measuring the temperature change from a ship or a drifter that is being affected by the current, so our temperature can change in both space and time. The first term is our Eulerian rate of change, or our change in temperature with respect to time. This is analogous to measuring the temperature from a fixed location and determining the temperature change at that location with respect to time. The remaining terms measure the temperature change in space, or the rate of change due to the spatial temperature gradient. For example, the change in temperature with respect to x that is being advected by current U. Together these terms describe the advection of temperature. Now, on our right-hand side of the equation, we have our sources and sinks at the surface of the ocean. This can be described by 1 over the specific heat of water times rho naught, all multiplied by the gradient of the net surface heat flux, or Q net. Surface heat flux only acts in the z direction because heat is only lost or gained across the surface. So we are left with only the change of Q net with respect to z at the surface of the ocean. Q net can be described by Qs, or shortwave incoming solar radiation. This is the heat gain into the ocean and is the only value that penetrates below a few centimeters. This can be added to QB, or long wavelength radiation, which is both an input and output of heat, but overall is a net loss from the ocean. We also have QE, which is latent heat flux, which is a flux out of the ocean, or a heat loss due to evaporation in the form of water vapor. And finally, we have sensible heat flux, which again is a flux out of the ocean, or a heat loss due to convection from temperature difference between the ocean and atmosphere. Our final terms in our heat budget equation are our eddy, friction, or diffusivity terms, and our molecular diffusivity terms. In this case, our concentration gradient is temperature. Okay, so our final property that we have talked about so far is salinity. The salinity budget equation can be written similarly to the heat budget equation, except this time our input and output of salinity is evaporation and precipitation. Okay, so those are our properties and tracers that we have discussed so far. We can describe the motion of water in a similar way by using the Navier-Stokes equations, which I will review in whole one more time here. Sorry it gets a bit messy here. I guess I'll upload the scanned version of these notes, which might be a little bit easier for you to read. Once again, we have our advection terms and our Coriolis terms on the left-hand side of the Navier-Stokes equations. But note that the Coriolis, again, is only in the x and the y directions. On the right-hand side, we have our pressure gradient term and our gravity term, which only acts in the z direction. And finally, we have our friction terms, which we know are either the eddy friction diffusivity terms or the molecular diffusivity. Again, I apologize for this being a little bit messy, but I'll upload the scans, and you know where you can find all of this in the notes as well. Okay, so finally I'm going to review a few of the balances that we've made over the last few weeks of lecture, just to sum up this video. First we have inertial circles, which is a balance between the advection terms and the Coriolis terms. The assumptions we make for inertial circles are rotating, frictionless, and incompressible. We've also looked at the geostrophic balance, the balance between the Coriolis and the pressure gradient term. For geostrophy, we make the steady flow assumption. We assume the friction terms are small, and so we neglect them, and we assume that our Rossby number is much less than 1, so our advective terms are small compared to the Coriolis term. By integrating from some depth z to the height of the free surface eta, we can put our geostrophic relation in terms of sea surface height. And finally, we can assume hydrostatic and make the Boussinesq approximation, which says that density variations are small and unimportant except in the gravity term. This allows us to derive the thermal wind equation, which relates the vertical gradients of the velocity or shear to the horizontal gradients of the density. Okay, so that's our quick basic review for today. For this week's forum discussion, I ask that you post a few questions about material that we have covered or something you want to review before the midterm. Please put some thought into it. We will cover as many topics in class on Thursday as possible. And don't forget that the short homework is due on Thursday, next Thursday. Awesome. Thanks, guys. See you on Thursday.